Okay, what I wanted to do here was to do an overview of the homework problems that you have assigned for Module 6, okay? Now, as we look here, just kind of as an overview before we get into the chapter, number one, you are going to be taking all of these problems out of the handout. This is the same handout that is in the learning plan, and this is that PDF that I attached here. Do not use the McGraw-Hill ebook, okay? Do not use those. This is chapter 6 out of this handout. The first three problems are trust problems. The first one, problem 6.5. We did get started on this the last time we were together. We did like half the manual calculations, if you would. We got started on the setup, and then you need to finish the manual calculations and attach the MD solids solution. Okay. So that one I know we got a really good start on the last time we were together. So I'm not going to re-go over that. Then what you're going to do is you're going to look at problem 615 and 622 on the pages that are identified here. And you're just going to do the MD solids solutions. Now, when you hand in the MD solids, you are going to be submitting a screenshot of those final diagrams with the values, okay? So you don't have to save the file if you don't want to, and you don't have to print it off. You don't have to print to a PDF. All you have to do is do a screenshot, okay? And that screenshot then will be submitted for that problem, okay? So if we look at page 114, it's going to be 615. You are going to be setting up in MD solids problem 615 here. Now, you are going to notice that you have a force that's at an angle. All right. MD solids will not allow you to add a force in at an angle. So as preparation for this problem, you're going to need to find the X and the Y components at B. So I'm just going to call this BY and BX. Notice that the force is going down and to the right. So the Y has to go down and the X has to go to the right. Okay. So there's going to be two forces that you're going to add, or two loads that you're going to add in MD solids at B. Okay. Broken into their X and Y components, as well as the 18 kilonewtons. And then you're going to, simulate it as you see here with a roller at A, a pin at B, and then the respective distances. Okay, again, screenshot for this. The only work that you really have to do manually is going to be determining those reactions at the supports. Okay. And then your second one is problem 22, 622. That's going to be on 118. And that is the truss that you see here. Okay, this one you don't have to worry about any X and Y components. You're just going to simulate it as you see it here. This is a roller, this is a pin, and then screenshot of those results. Okay, so any questions on the truss problems, which are the first three here? Okay. The next ones that you have here are going to be in regard to frames and machines. Okay. So I believe the first two are going to be frames and the last two are going to be machines, with this number 42 being a pulley problem. So let's take a peek at 630. This is found on page 126. Let me get over there. Okay. And as we look down here, now this is a frame problem. This is 630. And you're going to notice that we're going to be looking at a truck and a trailer, and then it's attached with a pin right here. So it doesn't look like a traditional frame, but it's solved like a frame problem, because if you would, you could simply show this as a member right here with the roller supports, a member here, roller support, and then they're connected by a simple pin. Okay. So this really is going to be solved exactly like a frame problem. Just so you know, there is a video in the session recordings for this problem. So if you did need to get, have a hint on how to solve it, or you wanted to get a little bit more direction on setting it up, that's going to be a great resource for you. Now it says here, same as problem 629. So the problem statement here is over on the left-hand side here at 29. So you'll see that it says a building contractor uses his utility trailer to bring tools and materials to various job sites. The trailer's loaded weight L, capital L, and that's going to be listed, I'm sorry, over here for this problem. Okay. Acts as if concentrated at its center and of the gravity as its center of gravity at E. So E is the center of gravity for the trailer, and in problem 630, that's going to be a force of 3,000 pounds going down. Tim, I notice you just had a when turning in, do you want two PDF values? That's a good question. I'm going to back up for that. So manual calculations only for the one problem. So if we go back to our application problems, you only need manual calculations for 6.5. You are doing only SolidWorks for the, or I'm sorry, MD Solids for the other two. And these are the screenshots of just MD Solids. So you'll notice that the first one, 6.5, is 20 points because you're doing manual calculations and handing in the MD Solids screenshot. For the next two, they're only worth 10 points each because it's only screenshots. Is that helpful, Tim?
Yeah, that makes sense.
Okay. All right.
Thank you.
You're welcome. I'm glad you asked that. All right, let's go back. I didn't want to forget about it. Okay, so that's L, that's the trailer's weight. That's going to be 3,000 pounds going down at E. And then you have distances here corresponding to the values that are here. All right. The truck center of gravity is at B, and W is going to be its weight. So in this case, it's going to be 6,400 pounds with then again, the dimensions as we see. So if the truck and the trailer are at rest and have the given dimensions, they want you to determine the force called the tongue weight that the trailer exerts on the ball hitch at D. So the trailer and the truck are going to be connected, and we're going to simulate it like a pin. I'm saying doing that in quotes, but what that is that's going to be the tongue weight. That's going to be the force that's going to go down on the trailer. I'm sorry, on the truck's ball hitch. Okay. For those who maybe, work with trailers and haul things around, that's a very common, way to say that. Then they also want you to find the force exerted by the ground on each of the two tires at A, at C, and at F. So each of the two tires. So when you find the reactions at each of these supports, which are 3 rollers, that's going to be on 2 tires in each position. So you would divide each one of those in half to find out what it is for each of those reactions. Okay. So that's problem 630. Again, doesn't look like a traditional frame, but because it's a pin connecting one segment to another segment, if you would, it is actually modeled and solved exactly the same way. Okay. So I'm going to let you get started on that one. And like I said, if you need any help, there is a video in the session recordings if you want to record it, or you can always ask when we get together. Okay, so that's number 30. The next problem you're going to be looking at is number 34. Number 34. Here is number 34, up at the top of page 127. Kind of put this here. There we go. Page 127. So here's a frame. This time you only have 2 members. You have 1 member here and 1 member here. 2 supports. They are both pin supports. So this is a pin and this is a pin. Okay. 3 external forces. And you're going to use that same process that we used for the frames earlier this evening. So you're first going to keep this together and you're going to try to solve for the reactions of the supports. These are in line with one another this time. Okay, just so that you know. All right. You're not going to be able to solve for all of them because there's going to be an X and a Y here and an X and a Y here. All right. So there's going to be something you won't be able to solve for. That's okay. Because remember, then you're going to break it into its individual members. And at the individual member level, you will be able to solve them. Okay, so use that process that we used on the example that we went over earlier tonight for this one. But again, I'm going to tell you, there is a setup for you in the recorded session for module 6 that will help you if you need a little bit of extra for this problem. Okay, so check that out if you need to. The next problem that you have is going to be a pulley problem. The pulley problem is 642. Now, there's actually 4 parts to this, so you're going to do 4 pulleys, okay? So you've got A, B, C, and D, all right? Now, as we had done in the pulley problems, always start with your load, and your load is going to be the W in each one of these cases. Now, for problem number 42, the problem statement is at the bottom of the first column, and the illustration is at the top of the second column. So for the information that you need here, it says W is 1.25 kips. They want you to determine P for each one, which is that pulling force that we pull down with on each one of the pulley systems, required to maintain equilibrium of the frictionless pulley systems shown and the reactions at the ceiling, okay? So if we look here, for some of these, there's more than one reaction. So there's 2 reactions at the ceiling here for A. There's 1 reaction here at B. This one's similar to the one that we did in the example. C has 1, 2, 3, 4 reactions. And then you'll notice that we have 2 reactions at the ceiling for D. Okay. Here again, if you need any help with these, there are some videos that help you set these up. Okay. So and then also you can ask in class as well when we look at these. So that's your pulley problem for the homework. And then the last one that you're going to be doing, it's going to be on page 129. The problem statement is at the second to last on the bottom, on the left-hand column here, but the illustration is looking at the bolt cutters that we see up here at the top of page 129. You're doing 647, okay? You'll kind of see it has the illustration here. This is going to be the same exact process as that last example problem that we did in module 6. So this is going to be for each handle of the bolt cutter shown acts as a simple lever, just like we saw earlier, for the dimensions and the input force given. And here are your dimensions, A, B, and PI. You want to find the force exerted on that pin B. And then you also want to find the force exerted by the handle AB to the bolt at A. So again, it's going to be the exact same setup. You're going to look at, if you would, one of the handles, putting a straight line through here, and then you're going to simulate it, just like we did, and then solve for what is the force on the bolt, as well as what is going on at that pin, the X and Y reactions. Okay. So, so the example problems that we did should have you, set up nicely to solve for each one of these application problems. So you'll notice here that then there's a total of 90 points, and then you want to hand it in by the due date. So are there any additional questions on the application problems here in terms of, what you have to do? Maybe not in the final answers, but in what you have to do. Okay, and turning in and such. So again, manual calculations and MD solids for the first one, MD solid screenshots only for these next 2. So no manual work here, but then our normal manual work for the rest. Okay, so if not, what I'm going to do is I am going to stop the recording.